Okay, so good morning to all of you over here on the Pacific Coast. Good afternoon to everyone else. Welcome to the May Exceed ECSS Symposium. We have two talks lined up today. The first one, or we're still waiting for our speaker to get here, is Reworking Inefficient Workflows for Shared HPC Resources, and that's going to be by Mitchell Dorrell from the Pittsburgh Supercomputing Center. And if the name and title look familiar, they should, because Mitchell was supposed to present at the last symposium, and then they lost power. I think they had an ice storm in Pittsburgh.
Okay.
And then our
no ice storm now, but Mitch says if folks are ready, he wouldn't mind them going first.
Okay. Yeah, so I think we're going to go ahead and is Mitchell here?
No.
Looks like he's still trying to get on. Okay, yeah, we'll need to proceed. And then our other presentation, a historical big data analysis to study the social construction of juvenile delinquency. This is the latest progress. We have four speakers: Yu Zhang, Sandeep Sathisan, Bhavya, and Adam Davies from CSU Fresno, University of Illinois Urbana-Champaign, and CSA. So just want to remind everybody that the ECSS Symposium is an Exceed event. So we are governed by the Exceed Code of Conduct. Once I turn things over to the speakers, I will take the URL for that and paste that into the chat. I'm going to go ahead and stop sharing now, and I'm going to turn things over to our speakers for the presentation that was listed second. I spoke to them beforehand, and they prefer that we save any questions until the end, and I will field them. So whenever you're ready, I guess Sandeep, you're the one who's sharing the slides. So go ahead and take things away.
Welcome everyone to our presentation on a historical big data analysis to study the social construction of juvenile delinquency. So it has the suffix latest progress, because we did a similar symposium in 2018 with the same title. So we are currently focusing on, in this presentation we'll be focusing on the latest progress that we had on this project since then. So this is the project team. Professor Yu Zhang from CSU is the PI on the ECSS project. Professor Cheng Jai from computer science leads the text analysis research and development. Alan Craig, you all know from Exceed, who is the person who connects the dots. I think he has been on this project right from its inception. And Bhavya and Adam are PhD candidates from computer science who work on the text analysis research and implementation. Matthew is an undergraduate student who works on the OCR part of things, and I work on the image analysis as well as data collection and some preliminary data ingestion into the databases. So with that, let me hand it over to you, who will start with the introduction. If you're speaking, you're on mute.
Sorry. Thank you, everyone. Our project studied juvenile delinquency from a social constructionism perspective. So first, why we started from the social constructionism perspective. In sociology, for a very long time, people look at the social phenomena from an objective perspective. However, everyone is participating in a social life, so it's impossible to look at the social phenomena only from an objective perspective. So instead, social constructionism contrast the external world with the human-created or constructed world. So we think besides the physical world, there is a world that's constructed by human beings. So there are three types of mental facts in the humans constructed world, like purely mental facts, social facts, or institutional facts. The crime and the juvenile delinquency belong to the social facts. So studying the juvenile delinquency from the perspective of social constructionism can provide us with a historical and a contextual view of the social problems. The second, why we choose juvenile delinquency. Compared to the traditional criminal activities, juvenile delinquency has a relatively short history and also relatively new in a legal history. So it can help us to collect the data. So knowing the historical and the contextual factors, we can have a comprehensive understanding of the juvenile delinquency, and also can help us to predict the future of the juvenile delinquency development. Second, next slide. But the problem is how we get data for this project. So newspaper stories can be a very good the data resources to look at the juvenile delinquency, because we can use news stories to look at how people define and describe the juvenile delinquency in their time periods. However, we have 100 years newspaper stories. So that's a big challenge for social scientists. But luckily, thanks for the XSEED and the ECSS, I know the Alan. Then Alan collected me to the computer scientists. So now we have a team. We will look at the juvenile delinquency by using 100 newspaper, not by the people by hands, but we use the big data analysis the system to use a system to analyze this problem and much easier and much quicker. So next, my team gonna introduce the specific of this project. Sandy, please.
Thanks, you. So, so I think so you described about the social science aspects as well as the newspaper data. So this is just a kind of like a progress update about like what happened in the first couple of years. So this project officially kicked off in end of 2017, early 2018, and at that point, like we kind of like defined the major phases that involved like data collection, image pre-processing and analysis, text pre-processing and analysis, as well as like query and visualization. So these are some of the major milestones from the initial 2 years. We started with gathering data from the Library of Congress, chronicling America collection. And soon after, we started identifying some issues with it. For example, like there was no article segmentation that was available. So we had to, start looking at that. And OCR text quality was good enough for the Library of Congress because, you're searching a word across a corpus to find some relevant articles. But, we think that, it could be better for a text analysis project where we are actually asking like specific questions about a problem. So, so we worked on the OCR, improving the OCR quality. We also like experimented with trying to identify article boundaries from the text as well as the text metadata that was available. And we gave our first ECSS Symposium talk in May 2018. And then soon after that, I think we got access to the ProQuest historical collection, historical newspapers, which is a different collection that I'll describe in the next slide. We also like published our like first like the poster paper in eScience at the end of 2019. So so on the data collection side, we, as I mentioned, like we are working with two data collections. One is a public data collection that is a Library of Congress one. The other one is a ProQuest, which has, so the Library of Congress collection has about 19.6 million records at this point. And we have downloaded about like 18.4 million text files and about 500,000 scanned newspaper images, and using their bulk API. And all of this is currently stored in the Exceed Bridges 2 machine. So we used the Bridges 2 compute node, and we used Python with some parallelism to use like all the nodes, all the cores that are available in that node. ProQuest is a digital archive that that offers like full text and as well as articles, and it dates back to 18th century. The difference here is that it contains newspaper data that are not in the public domain. So which means that the data itself comes with certain restrictions on what we can do and what we cannot do. So we had to, for example, we had to do the processing, all the processing within the Illinois systems, because the data could not be like moved out of the Illinois machines. We are using about like 58 million records from this collection. So going to the next module or the phase, image analysis. In the last few years, we have been like focusing mostly on the newspaper segmentation aspect on the Library of Congress collection, because that's where I should also mention that the ProQuest collection also already comes with segmented articles. So we didn't really have to do any segmentation there. But so we focused on doing newspaper segmentation on the Library of Congress collection. For that, we are using a transfer learning approach using the mask RCNN model that's pre-trained. You can see that the training and the validation sets are small, but it took a lot of time to even annotate this, because we are talking about like large images and annotating like small regions and differentiating between like articles and ads and things like that. So for this purpose, we actually used NCSA HAL cluster, which is a specialized machine learning cluster that's available. I think it was just more a reason of a convenience that we used it. I know the same analysis could be because I had already undergone some training on the HAL cluster. So and I already knew about some tools that are available there. So I just used the image analysis programs there. But we'll be like porting whatever we have developed into Bridges for actual processing. These are some of the recent results from the image analysis or the newspaper segmentation. You can see that with that even with that small data set, we are getting some good results when it comes to segmentation. It might not be very obvious, but here it's actually differentiates this particular region as an ad, for example, a different region as a photograph. But there are also some issues, like you can see some overlap, even though like in certain times the articles kind of overlap. But we think that this is like good enough to get started with processing the Library of Congress collection, because it is kind of like again like generally getting a good sense of like different article regions and different types of newspaper segments and things like that. So we are kind of like moving forward with what we have, and also like trying to improve the model parallelly. What you see here is an example set of individual segments that were generated using the same mask RCNN model. So the RCNN model gives us the segments, and this is just a crop of that. Again, you can see like some issues like the heading cutoff, but again, kind of a broad sense is that this is like good enough to move to the next phase of doing like re-OCR on this collection. So these are our current and the next tasks. So currently we are looking at Tesseract on the segments to do OCR. We had earlier looked at Tesseract at the entire page, and we saw some limitations there. Now we are looking at just the individual segments and trying to do OCR on that. We are also like working towards getting this the model to run in Bridges to process the entire collection. The next task would be to actually complete the processing, as well as complete the re-OCR, either using Tesseract or using like Cloud Vision API that we had used earlier for some evaluation purposes. So with that, I think I'll hand it over to Bhavya, who will start with the text analysis sections of this presentation.
Yeah, thanks, Sandeep. Yeah, so once we have a good set of segmented images identified, the next step is to process the text of the articles. So the overall goal here is to understand this concept of juvenile delinquency better. Specifically, we have two goals. The first is to search the historical articles about this concept. And we developed two main techniques here, human-in-the-loop retrieval and adapted topic modeling for this task. And secondly, we want to analyze the changes in meaning and usage of this concept over time. And for this, we leveraged a tool called Shiko and also developed an algorithm which uses CCLA. And we'll go over all of these next. So the first tool that we used for searching is called Kibana Search. So this is a publicly available tool. And on the right-hand side, you can see one interface that it provides for searching for articles. And you can customize the time period that you want to see the results. And if you want to compare multiple search queries, you can define the search queries that you want to search for. And this is one of the sample time series curves that it gave us back. So here, the green curve is for the term juvenile, and the brownish curve at the bottom is for juvenile delinquency. And the graph is showing the proportion of articles that contained these terms over the years as per our data collection. So we can see that initially juvenile delinquency wasn't really mentioned in the newspaper articles, whereas later the two curves kind of closely mimic each other. So suggesting that the terms had a deeper correlation later as the years went by. Next slide. Then this is the overall framework that we use, called Human-in-the-Loop Retrieval Framework. So the retrieval component has specifically two kinds of approaches that we've explored so far. One is unsupervised, mainly query expansion, and then the Kibana search that I described previously. So on the left-hand side, you can see the interface that we developed for this. So for example, for the term concept juvenile delinquency, the tool would suggest to you some synonyms based on our word-to-vec models, which learn the similarity between terms. And then from the synonyms, a user can select which ones they want to query our data collection. And then the tool then generates a query in the Kibana search syntax. And so then we can directly use this query and get back the results from Kibana. And once we have the results, then the user can go in and even do some annotation, like is shown here on the right-hand side. So they can mark which of the search results are actually relevant for the use case, and also make some notes there, like highlight some specific segments that are most relevant. So this is kind of a loop where humans can continuously guide the machines. So for example, this annotation can be used for training text classification models, which again return some results. And then again, this like loop keeps on going continuously based on how accurate or interesting the user wants the results to be. Next slide. This is another kind of toolkit that we're using called topic modeling. So this is a probabilistic model LDA that we are using. So we ran this algorithm multiple times on our data collection with different subsets of the data or different configurations. And here we're showing some sample crime-related topics. So these are just lists of words which contain some terms like prisoner or court and so on. And since these groups of words can sometimes be hard to interpret, and it can be hard to identify the exact context where these words were mentioned in the data collection. We also show a topic overview on the right-hand side that shows the most relevant sentences. So for example, this sentence had a topic coverage of 98% to these crime topics. And we can see it contains terms like prisoners, jury, etc. So this is another toolkit that social scientists can use for exploring a particular concept more and identifying which topics are interesting, and then further use the identified topics to search more articles that are similar or contain that topic. Yep. Next slide.
And so the next, oh, sorry, go ahead.
Yeah, go ahead. Adam will describe the remaining text analysis segments.
Sure. So Chico is another part of our data analysis pipeline that we designed. So we're using this existing tool that can allow us to easily visualize changes in associated terms over time based on trained word embedding models. So you can see, for example, on the left-hand side here in 1824, that there isn't a clear association. So associations are denoted by edges in the graph. You can see that there isn't an edge between juvenile and delinquency in 1824, but there is in 1924. And you can see that there is a change in sort of the general terms that are used that are most associated with each of these individual terms. So for example, sprightliness, pleasantry, vivacity, or something on the left hand on 1824 versus 1924, we might see words that are somewhat more reflective of the contemporary context, like criminal, adolescent, psychopathic, and so on. Let's go to the next slide. And so another way that we can apply these word embedding models is using an algorithm that is called CrossContext lexical analysis. And so the goal here is essentially to directly quantify the semantic change over time instead of just looking at specific terms that are changing in terms of their association with some query term like juvenile, delinquency, or young offender. We want to sort of measure in the aggregate how much is the representation of the meaning of a term or a cluster of words, how much does it change over time? And so the essential principle here is that we're looking at the nearest neighbors in this word embedding space and saying that those are the most associated terms, like we saw on the last slide with those little word clouds. What are the most associated terms in a given period? What are the most associated words in the next period? And we compare essentially what is the overlap and the degree of similarity. And then by plotting that over time, you can see a general sense of how consistent those word representations are over time, at least as a function of the word embedding models that we train them on. So if we go to the next slide here, we can see on the left-hand side that plot that I'm talking about. And you can see, for example, that these peaks in the graph refer to periods of relative semantic stability, whereas sort of the troughs or the dips are periods of relative instability or semantic change. And so, for example, I have here on the right-hand side a couple of periods where there was a period of rapid change. So, for example, we see in the 1840s, things like criminals, of course, we see vagrancy, prisons, gaols, which is another word for jails, and so on. And then in the 1890s, and sort of that period preceding the 1890s, where there was a higher period of stability, reformatory and reformatories appear very near the top of this list, suggesting that the use of reformatories that was prominent during that period also really pops up in the newspapers. And then sort of in the 1910s, you see reformatories moving back down the list, and you start to see things like defectives and truancy coming into play. And so on the left-hand side, we have a direct quantification of the degree of semantic change. And on the right-hand side, you can sort of easily zoom in on a specific period and say, okay, well, what word associations changed in that period? Next slide. And so there's some remaining work to address the sort of social construction question that we're very interested in. Our next steps are first to use a lot of the retrieval components that we talked about to assemble a text collection describing juvenile behaviors. So that's including, but it isn't just limited to juvenile behavior or juvenile delinquency. And we want to run some topic models on this collection of sort of texts related to juvenile behaviors and see if we can identify individual topics that correspond to different forms of social construction per some of the social construction theories that we're interested in. And we also want to finally analyze the relationship between the learned word representations in each period and over time. We want to compare those to the topics in order to get a better sense essentially of how the representation of individual terms changed in terms of their association to these different social construction categories. And so this is a specific use case that we've built sort of the whole system around, is looking at the social construction of juvenile delinquency. But we see a sort of a broader framework that we're exploring. The tools are fairly general purpose, and a lot of the design principles that we employed in constructing this system we think are also quite general. And so hopefully in the future, we'll be able to extend this to additional social science research questions. Next slide.
Okay. Thanks, Adam. So to conclude, I think we have experimented with a very highly interdisciplinary project that combines like criminology with image analysis, text analysis, computer vision, general computer science algorithms, and I think like the journey has been like very very interesting in the last few years. And on all the major like phases or the modules, we have made like significant progress. Now we have like 2 major collections that we have access to, and also like on the image analysis side, we have like the segments that are getting generated. Now we are working towards like doing like OCR on the individual segments. On the text analysis side, like we have developed methods for performing like semantic search of historical articles about juvenile delinquency, and also like explored and also like developed tools to analyze these changes about the juvenile delinquency related terms. On the query and visualization side, you've already seen that we have already started generating some interesting visualizations, and there'll be like continuing work towards like answering specific social science questions, and also to realize the vision about this larger like generic purpose social science a platform that uses like big data analysis tools. These are some of the additional references that we have used in this presentation. And again, a list of acknowledgements here. You can see like we have used a wide variety of systems, including Exceed systems, ECSS support, as well as like UFI systems, and also like in-house systems within computer science department. And we got the access to ProQuest through the Client Center and the University of Illinois library. We thank all the all the help that we got. And here we have an upcoming publication in the Platform for Advanced Scientific Computing conference, where we'll be like going through all the details about this this project, right from its beginning and its current state, about the system that we are building, its architecture, the future work, and everything. So please watch out for that. This will come online in June. And with that, I think we'll take any questions. Thanks for listening.
Great, thank you to our 4 speakers for that excellent presentation. Do we have any questions? All right, if not, I will kick it off with one question. So first of all, this is fantastic. There's so many parts. There's the the image segmentation, the optical character recognition, the actual deep learning techniques, and so on. But with the segmentation of the articles, how do you handle articles that span multiple pages? So something that starts on page 1 and then at the bottom it says, continued on another page. Do you link the text together? Do you say go by that reference, or that points to page 5, or is there something a little more complicated?
Yeah, I think I'll probably answer part of that question, and because part of it is like image analysis, and the part it is more about like text analysis. So I think like on the image analysis side, we have the current work actually looks at the article boundaries and splits them. We are aware that there is that situation where when the article continues to a different page, we kind of lose track of that. We have metadata about like what was this original page that it came from. So I think like we had some discussions about like using again some sort of text analysis to combine these individual text segments and then try to like group them, and maybe like and then that would be like an additional research to kind of like figure out like, have we segmented it too much? Have we like split an article multiple times? So I think that's definitely a topic that came up. But I think the current setting, we are just looking at the broader segments, and then maybe as a future work we'll be, I guess, looking at combining like different segments that spans across like multiple pages.
Great, thank you. And Sergio, I see you have your hand raised. Do you want to go ahead and ask your question?
Yes, thank you. Thank you, everybody. Fantastic talk. I was just wondering, I guess you have certain hypotheses or, informed by theory. is there kind of an algorithmic way that you could specifically say, here's my hypothesis, and have that kind of algorithmically guide the analysis of the data so that you can see, maybe a probability to which, with which the, hypothesis is confirmed? Because I think social scientists kind of like to look at it like that.
I'm not yeah, I'm not completely sure about the specific probabilities, or that kind of metrics. But maybe you or Adam, would you like to comment on that question?
Yeah. So now is still an exploratory stage of the part, but the basic hypothesis is that juvenile delinquency is actually a social constructed concept, and the definition and description can change during the different time periods because of people's the recognition of people's claimation. So it's just not only a physical existence, but it's a mental concept, constructed by the social life. So I think Adam can talk about how the text analysis has showing in current status.
So the very fact that the change of terms over the decades is visible, that's already something that in the social science context is is important, right?
It's still very new in the social science because as a social scientists, we don't have the training of the data. So this study is still a pioneering study. So we're really interested to see what kind of the results coming from this project. So we can probably not only study a limit to the juvenile delinquency, but we're going to expand our research to other social concepts to answer other social questions.
Okay, thank you very much.
Thank you.
And I see we have two more hands raised by Amy and Mitchell, but we're running a little short on time. So Amy, Mitchell, let me ask that you follow up with speakers later. Maybe you could do this through the chat. And we need to turn things over to Mitchell Dorrell. So Mitchell, when you're ready, go ahead and share your screen.
My name is Mitchell Dorrell. I work at Pittsburgh Supercomputing Center. I'm part of the User Support for Scientific Applications team. And the discussion I'm going to be sharing with you today regards how to rework an existing open source project to be more efficient on a shared high performance computing resource. Now, I want to give a very brief caveat here. My background, while it is in biophysics, it's not in proteins. So this adventure into the world of AlphaFold and protein folding is quite a bit unfamiliar to me. As a result, this focus is going to be on the technical aspects of how to decompose an application rather than the scientific aspects of the protein folding tasks themselves. So if you're interested in an overview of the details for how this works, unfortunately, you'll need to find that elsewhere because I'm not qualified to give that. So with that said, let's start with what is AlphaFold? So at a global level, AlphaFold folds proteins using artificial intelligence and deep learning. The main input file is an amino acid sequence, which is given to it in the FASTA format. But to be fair, it also has several other input files in the form of genetic sequence databases. This is generally it's a little over 2 terabytes worth of public genetic databases that AlphaFold uses to inform its decisions. So while these databases are also technically input files, they're not something that the users typically change. They're pretty much a constant throughout the process, throughout different use cases. And the output file is an atomic structure in the PDB format, which is basically a list of atoms and their coordinates and a couple other details. But this is the main task that it was trying to solve. You give it a sequence, and you get out a structure. That's in the past that's been known to be notoriously difficult. Notoriously difficult to automate specifically. So much so that the typical way to do it is generally just humans folding proteins by hand using some special tools. It wasn't until AlphaFold came along that there was a computer method of folding a protein that was as roughly as accurate as humans doing it by hand. A couple more details about AlphaFold. It's developed by DeepMind, which is a subsidiary of Alphabet. It used to be a subsidiary of Google when Google restructured itself. DeepMind became a subsidiary of Alphabet instead. It is written in Python, and it's distributed on GitHub. Specifically, there's the link. You don't need to write that on. If you Google AlphaFold GitHub, it comes right up. So to explain a little bit about how AlphaFold works, this is just a very, very broad overview. You start by giving it a FASTA file. That's your genetic sequence, the sequence of the protein that you're trying to fold. Once you have that FASTA file, you feed that into AlphaFold. It will then go through a few different processes. It will feed that FASTA file into Jackhammer with using it to search through the UniRef90 database. It will feed it into Jackhammer a second time to search the MGNIFY database. And then depending on your settings, if you choose to use the full-size databases, it will also feed it into HHBlitz to search the BFD and UniClus30 databases. Where if instead you use the small the reduced database commands just to try to perhaps do a test run to get a result quicker, which is generally not going to be quite as accurate, but can still be useful. In that case, it does not run HHBlitz, but it runs Jackhammer again, using a special reduced version of the BFD database. In addition to running these Jackhammer and HHBlitz commands, it also takes the output from the UniRef90 call to Jackhammer, and it has to convert the output file to a different format so it can feed it back into HHSearch, which it uses to prepare a selection of templates that it also uses to inform the model generation. So once it's got all these different processes run, it feeds the templates from HHSearch and 3 different output files from the 2 Jackhammers, and then the third thing being either from HHBlitz or Jackhammer. It feeds all of those into a final subroutine that actually prepares the models and calls the AI tasks. The important thing to know here is all of the rectangles that are highlighted in red are external tools, and they are slow. They are CPU bound and IO bound. They typically only use a couple of CPU cores. They don't touch the GPUs at all. And let me just reiterate, they are slow. The final phase where it's preparing the models, that's where it actually goes ahead and invokes the GPUs and can, that's when you're actually doing the interesting AlphaFold sequences themselves. The original AlphaFold novel routines are in the prepare models phase. So the problem is, this is what we're looking at in terms of the timelines here. So the way AlphaFold breaks it up, AlphaFold gives you just the overall features breakdown timeline, and then the 5 models it generates at the end. It shows you the times it takes to do each of those. One of the things I did is I created some customized scripts just to dump out the individual times used for these different routines that it's calling out to. If we compare this to the previous slide, the HHBlitz indicates that this was run using the full-size databases. So this is an example of a full-size database run using an example FASTA file. And essentially, you can see it runs Jackhammer using the Uniref 90 database first. Then it'll run, once that finishes, then it starts Jackhammer for the MGN IFY database. Once that's finished, then it will take the output of the first Jackhammer, and that's the S indicates the HH search algorithm. And then finally, it runs HH Blitz. That's that last input. So then it takes all those outputs and then uses those to start generating the models. But the only part of that beginning of those 4 slow processes, the only part that actually has to be done sequentially is HH search. The S has to run after the Uniref 90 Jackhammer. That's the only part that must be run sequentially. Everything else can be run in parallel. And then, of course, all of that is necessary to be, before the models can be computed. So this poses a big issue because if we want to run this on the GPU nodes at a supercomputing facility, if you submit a typical AlphaFold task, to the job scheduler that uses these, that calls out to the GPU nodes, for example, it'll assign the task to a GPU node, and then while these first roughly 235 minutes or so of the features are being computed, the GPUs are just sitting idle. They're not doing anything at all. So the first 235 minutes in this case completely waste the GPU altogether. Now, I want to make a mention here that this is an example FASTA that is very short. For longer sequences that are more realistically going to be of interest, this could take hours, or depending on the resources, it could even take days. So we're talking a significant amount of GPU time being completely wasted. The GPUs only get started around the 235 minute marker. And so the better way to do it, if we would hope, it would be to just occupy the GPUs, just reserve the GPUs during that last section, while telling the scheduler that all the beginning parts only need CPU usage. But the problem is, this is one command. You run AlphaFold, and it just runs the whole sequence. To give a little bit more context, as an example resource, I'm going to use Bridges 2 at PSC. We have a few different partitions that would be of interest to people running AlphaFold, ideally. First, we have the RM partition, which has 488 nodes with 128 CPU cores per node, but it does not have any GPUs in there. So preferably, we would like to have the CPU portions run on the RM partition, where it can run them most efficiently. There are a lot of nodes there, so you shouldn't have to wait in the queue for too long. And even if you are only using a couple cores at a time, we also make available an RM shared partition. So that way, maybe your process will only use 4 cores instead of 128. Then you can use RM shared so that you're not burning 128 service units every hour. So between RM shared and RM partition might be more suitable if you want to batch a bunch of sequences together. Then you could perhaps reserve a whole node and run maybe 25 or 30 sequences at the same time. Whereas RM shared might be more useful if you want to run individual sequences. And then in addition to the RM partition and the RM shared partition, we also have the GPU partition that has 33 nodes. They only have 40 CPU cores per node, but they have the 8 GPUs. So not only are the RM partitions more suitable just because they don't have GPUs, they're also more suitable because they have more CPU cores. So you can actually run more of the CPU stages in parallel on the RM partition than you can on the GPU partition. And then the final partition that might be of interest, depending on what you're doing and if your benchmarks make it worthwhile, we also have a GPU shared partition, which could be used if you only want to use maybe 1 or 2 of the GPUs instead of the full 8 GPUs on a node. So with these different partitions and the structure of AlphaFold, what I set out to do was to break up AlphaFold into different components. I wanted to prioritize the user experience, I wanted to make sure that if someone is reading a guide online for how to use AlphaFold, I want them to be able to more or less follow that guide without modifications. Obviously, there has to be some modifications because we're asking them to run some things on certain nodes and some things on other nodes. But the point here is that while there are some other tools out there, there are some other forks of AlphaFold, such as Parafold and a couple of others that are skipping my mind at the moment, that seek to accelerate or improve the parallelization of the CPU portions. It's hard to guarantee that the output of those forks will be exactly the same as if you ran AlphaFold normally and just waited patiently. So with the goal of replicating the original AlphaFold workflow as well as possible, I decided to change the Python code itself so that what would happen is, I'm going to reverse a couple of slides here if I can. So what I did is I modified the AlphaFold code so that whenever it reaches one of these red blocks, if you have passed a special parameter, a dry run parameter, instead of running these commands, calling out to these external tools, what it will do is it will print the command instead. So this will show you exactly the command that AlphaFold was going to run on the Uniref 90 database, exactly the command that it was going to run on the Nginify database, etc. It's going to show you all the exact commands. Now, because you can't run the HH search directly with the output of the jackhammer, with the Uniref 90, you have to run it back through the conversion. I had to add another subroutine that would just run the conversion. Basically, it just takes that little excerpt of the AlphaFold 2 code and allows you to call that independently. So the intention here is you will run AlphaFold with the dry run command. It will show you all the steps that you need to do. You will queue up Jackhammer and HH Blitz in your scheduler. And then you will also, how you want to do it is up to you. You could do it at the beginning of the HH search, or you could do it at the end of Jackhammer Uniref. You do need to call the conversion command. The conversion command is not computationally intensive. It's just a quick file adaptation. And then once all of those are finished, then you can pipe it all back into a final call back to AlphaFold 2 with another special parameter that I'll show you in a moment. Now, I had originally planned to do a live demo, but granted my luck with technical difficulties lately, I've decided that it's probably wise to skip that. So instead, I've included the example output. Oh, I'm sorry. I need to skip back to the end. Here we are. I've included the example output for what it looks like when you run AlphaFold with the dry run command. So as opposed to a standard AlphaFold procedure call or a command call, the only modification you make here, I hope my cursor is visible. I'm not sure that it is, but you'll see right after, at the top line, right after AlphaFold.sh, I've added the -- dry run. That's the only change you have to make. All of the other parameters get fed through AlphaFold in exactly the same way. So any parameters that DeepMind recommends, any parameters that you see in a tutorial, they will work exactly the same way and have the exact same effect. Once you run that, it dumps out all the commands in order. You can see you get the two jackhammers. The first one on the Uniref 90 database. Second one is on the, okay, thank you, it is visible. The second command is on the second jackhammer command is run on the MGY clusters database here. And like I said, this is exactly the output that you would get from, this is exactly the command that Jackhammer would run, or sorry, this is exactly the command that AlphaFold would run itself. So literally, there should be no difference in functionality between running these commands yourself and running them automatically as part of AlphaFold. Once you have the output from the Uniref 90 database, then you can call this command, which you call the dry run again because that activates my subroutines. And then I've added a conversion parameter here. You give it the input file, which is the output of the Uniref 90 database. and you tell it where to output the converted file, which ends up being used as an input to HH search, which you can see here. And then after all that's done, it calls one more, it's got this last jackhammer call. And then once you have all of these output files, you call the you basically call the same thing, the same command you originally did, but with the prep models parameter added to the end. What that does is it tells AlphaFold to look in the output directories that it told you about. It's got a standardized layout for the output directories, and it's going to tell AlphaFold to go through, and every time it encounters one of those red rectangles, now instead of running that, it's just going to read in the output file directly from disk instead. Once it has all those loaded into memory, then it can run it can actually prepare the models as expected. Now, this is a little bit unclear. This is what I'm going to call the raw format. As the most obvious future work that I intend to do very shortly is to make it clear how these commands need to be run. For example, the HH search must happen after the first jackhammer command, but all three jackhammer commands can run in parallel. And finally, that last alphafold.sh call has to be done after everything else. So in addition to clarifying that, I also intend to make it very easy for users to use by having it write out, in addition to dumping these example commands to the screen, what it will also do is it will write out example Slurm files, which will be configured with the dependencies already set up. So that way, it'll be a very simple one command. They can submit the jobs, and it will automatically run the correct tasks on the correct nodes and tell the job scheduler that certain tasks have to come after other ones. Slurm has built-in support for those features. It's pretty straightforward to do, but in order to make it as easy as possible for users, that is part of my intention. Because the dry run parameter itself, this original command that just dumps all this data out, because that's not computationally intensive, that can be run on a login node. There's no reason to submit that to a scheduler. But all of the subsequent commands should be scheduled. So I know that there's a lot of information on the screen right now, a lot of these different commands. There's some of these different parameters to jackhammer. Like I said, my background is not in protein folding. I cannot tell you the meaning of each of these individual commands. However, for users who do know what these commands do, they are welcome to edit them as well. Or if they have another method of generating these same output files, they can just ignore the AlphaFold's recommendations and substitute it for a different command that maybe suits their needs better. So the intention here is to increase flexibility and increase the efficiency for deploying on systems like Bridges 2 by extracting these commands directly and giving users an alternative way to run them. So with that said, I'll leave this up on the screen while I take questions.
Great, thank you, Mitchell. I'm so happy that you were able to get all of the technical issues worked out and presented today.
Yeah,
so
this
do we
is
have any
super
questions?
bizarre.
Yes, there's one here from Sandeep.
So that is an option. Yes. We're not going to configure it to submit the jobs for you because at the very least you will need to add in your own account ID so that it's charged to the appropriate place and things like that. But yes, it will provide you with the batch scripts so that way you can submit them on your own. And yes, they will have some. They will have the interdependencies already specified in the scripts. I see the next question. Is there an open source repository? There's not yet. This absolutely will be open source. My first goal is going to be to try to upstream it directly to DeepMind. I don't know how open DeepMind is to accepting these types of changes. In theory, they say that there's a procedure for submitting these types of improvements. But the idea here is if they welcome the changes, then will have it upstreamed, and then whenever they release the new version, you'd be able to take advantage of these parameters yourself. The next question I see, is there a patch that can be applied to other versions in 2.1.1? So 2.1.1 is the version that I was testing with. So most of these changes, I don't believe most of the changes that I've made affect code that has been improved in, I think there was 2.1.2 and 2.2.0. I'm not sure, I will have to check that. But as part of the upstreaming process, I will definitely have to port these changes forward to more recent versions. And then also once, as part of the upstreaming process, it will be very easy to generate the patches for whatever versions people might be running. I don't know how far back I can go without encountering some issues. But the one thing I didn't mention during the presentation is, for simplicity, I only covered the monomer pipeline. There is a multimer pipeline as well that's got a couple extra steps in it, but the same ideas apply.
And Mitchell, we're at the top of the hour now. I saw there was one more question from Rebecca. So if you don't mind, if you could answer that one, follow up offline. Okay.
All right, sure. Yes, so my email address is mwd@psc.edu. I will put that in the chat. Oops, I sent that to one person by accident. Let's try sending it to everyone. Yes, please feel free to reach out, and I will be happy to collaborate and explain how this works or assist you with running it on your own machines.
Great, thank you so much. Oh, go ahead.
Yes, I see another question coming in. Is it appropriate to answer it?
You know what? We're already a minute over, so let me ask you to follow up with that one offline.
Okay. All right. So yeah, please just reach out to me via email, and I'll be happy to address the question. Sure.
Great. So again, Mitchell, thank you so much, and thank you to all of our speakers from CSU, Fresno, University of Illinois, and NCSA. We're going to try to get the slides and the video posted shortly, and hope to see you all again in June. Thank you so much.